Good morning, everybody. Today I'm going to be competing in Codeforces Educational Round 92. It's not rated for me, it's rated for Div 2, which unfortunately doesn't include me. And I'll be walking through my thought process as I compete. If you're interested in the solutions, you can skip to the end of the video. I'll put timestamps in the description, and then you can see the solutions to the problems you're interested in. Otherwise, good luck, have fun while you're competing, and I'll see you on the scoreboard. All right, problem A. We know what the LCM is, given two integers, L and R. Find two integers between them where the LCM is also between them. Can we pick, oh, they have to be different. The answer might be -1. All right, what about L and L times 2? I think L and L times 2 always work. Yeah. The answer is L and L times 2. Oh, hello. L times 2 if this is greater than R. -1 for both. Otherwise, one, 2. Yeah, okay. Sounds good. All right, we have some array of n positive integers. Initially, you're standing at index 1 and have a score A1. You can perform two kinds of moves. You can move right, and add the next thing to your score. Or you can move left and add the previous thing to your score. Also, you can't perform two or more moves left in a row. So you can go back and forth as much as you'd like, but you can't ever go left twice. There can also be at most z moves among them. That's kind of confusing. Almost 5. That's weird. All right. You're given some array consisting of 3 integers, n, k, and z. Number of total moves. What do you print? The maximum score you can achieve. So you could do this with a dp. It's not circular because there's this limit on z. It's a bit tedious though. For problem B, usually there's a more straightforward answer. So here we can perform at most 4 moves, or exactly, you want to perform exactly k. What if that's not possible? Yeah, what if the answer is impossible? Because, like, you can only move right and move left, right? You can't sit still. So what if you can't, like, what if they want you to move 10 times, but you can only move right twice, and then you're not allowed to move left because z is 0? This if solves. I don't know that I understand the problem. For each test case, up at the maximum score you can achieve if you make exactly k moves total, no more of z of them are left, and there are no more than 2 left moves in a row. I guess I'll ask a clarification then. Oh wait, do we start at the leftmost position? If so, this is a stupid question. Start at index 1, and you make fewer than this many moves. Got it. Yeah, so we can do a DP. So you can always make k moves, because you could always just move right as many times as you want. And you can do a DP at your index times z times what you moved last. So that's the idea. Static int dp, or I guess we'll call this go. Index, also int at, like this is which, or I guess, no, that's where we are. Int z will be the number of, that doesn't work because it's n times k, I think. No, it's not n times k. Because the number of moves can be extracted from the number of left moves we've taken. Yeah, so int z, or int left allowed, int left last. And then also int moves left. Okay, so if dp at, let's reorder these so it runs faster maybe. Okay. dp at left allowed, left last, index is not equal to -1, then return that. Okay, if moves left is equal to 0, then return 0. Yeah. Or I guess it should probably be longs. What are these values going to be? How big are the values? 10 to the 4. So we should, wait, 10 to the 4 times 10 to the 5th is fine. Okay. So if we're out of moves, then we're done. Otherwise, if last left is equal to 0, and the index is greater than 0, and also left allowed is greater than 0, then we can move left, otherwise we can move right. Okay, so best equals 0, turn dp at left allowed, left last, index equal to 0, or equal to best. Alright, so now best is equal to the math.max of the best, or how much will this be? Okay, so we'll have left allowed -1. We just have traveled left, and then we'll be at index -1. So we get the maximum total we get from that, plus we get the array at index -1. And then the moves left will be, I guess, moves left -1. Good. And now we also want to move right. That's the other option. So it's either left allowed because we didn't move left. We'll go to the next index. We have one fewer move, and then we can go to index +1. So these are the two cases. This isn't an else though. This is if index is, well, this is just always true. You'll always be able to do this because of the properties of how big input is. So now int n equals this. What else are we given? Int left allowed equals this. And then this is total moves. Int moves left equals this. Okay. dp equals new int array n, nope, left allowed by left last, or by 2 by n. Right. Very good. So now yeah, +1 here. that should be fine. Okay, so now int ants equals go. Oh, we need to root in the array. Yeah, int ants equals go from left allowed. We had not moved left in the beginning. Well, actually, we could say we did move left, but that shouldn't matter. Index 0, and we have moves left. That's our answer. Oh man, I'm wrong. Okay. Oh, do we start with AI points? There you go. Okay. Ants plus 80. 15, 19. Yeah, okay. Thank you. 15, 19, 150, 56. Sounds good. How many test cases? 10 of the 4. We should be fine there. Stack Overflow might be an issue. Well, usually... how do we do this? For int at equals 0 at equals and next one at greater than equals 0 at minus go left allowed left 0 index I moves left. We don't know, so that's kind of annoying. Yeah, do we need stack trick? I guess it doesn't hurt. Why not? Okay, now new, or just call M. Looks, oops, what have I done? Yeah, it looks fine.
Well done, sir. AC on.
Okay, we got B. Let's move to C. Good string. Let's call a left cyclic shift to some string this other thing. So basically you take the first thing, move it to the end. Additionally, let's call a right cyclic shift the same thing, you just do the opposite. Let's say a string is good if its left cyclic shift is equal to its right cyclic shift. You are given a string n which consists of digits this. What is the minimum number of characters you need to erase to make it good? Minimum number of characters we need to erase, huh? Well, let's think about that for a moment. So if it's all the same character, it'll be good. If it's 2 characters, it will also be good. Let's try 3 and 4. So if you have 1, 2, 3, the left cyclic shift would be 3, 1, 2, and then you also have 2, 3, 1. So you have 1, 2, 3. 1 and 2 need to be the same. 2 and 3, 1 and 3. So this is all the same component, which means if it's 3 long, it all needs to be the same character. Is this always the case? I think so, because if you move this to the left, well, this is the first character, right? The first one. Yeah, so I think this is true for any odd. We can do it with 5 as well, I guess, maybe. Just to convince ourselves. 1, 2, 3, 4, 5 would lead to 2, 3, 4, 5, 1. and then also 1, 2, 3, 4 with a 5 in the beginning. So yeah, you can go 1 to 3, then 3 to 5, 5 to 2. So you just keep adding 2, and then you hit everything. So if it's odd, then they all have to be the same length. So now I suspect evens will be different. So if you have 1, 2, 3, 4, then you can get to 2, 3, 4, 1, or this. So now you have 2, 4, and 4, 2, and also 1, 3, and 3, 1. So if it's an odd length string, they all need to be the same. If it's even, you need 2 groups of equal size that are the same. So odd, 1 character, even. You can have 1 character, or also you can have 2 same size characters. Okay, so that should be very easy to code then. Int, or how is input formatted? Just a char array. So you've got this array, and now, yeah, let's do a counts. So increment this character, raise that sort counts, int max length, because we want to try and do this as much as possible, and then at the end we'll print the, yeah, okay, equals 0, whatever, and then this out a.length minus the max length. That's how many we'll need to delete. So now, this is going to be the math.max of 2 things. We can either do counts at counts.length minus 1, or we can do 2 times counts at counts.length minus 2. I think that's fine. Ooh, not right for this. So we need to delete 5, I say. Oh, because the order matters? Yeah. The order is important. Okay, so, yeah, so that's one option. So we can do this. The other thing we can do is we can just brute force what those 2 characters are, right? Because it's got to be first and second, then first and second. Let's just triple check that for like 6 maybe. Or maybe 8 is the right way to do it. 1, 2, 3, 4, 5, 6, 7, 8. First one is 2, 3, 4, 5, 6, 7, 8, 1, and then so 8 plus 2 is 2, 4 plus oh yeah, 8 plus 2 is 2, 2 plus 2 is 4, 4 plus 2 is 6, 6 plus 2 is 8. Yeah, so it needs to alternate A, B repeatedly. Okay, that's a good catch. So, okay, so if, well, yeah, so now length, or length minus equals len mod 2, because if it's odd, we want it to be even. Now for each of these characters, okay, so if len mod 2 is 0, that means we're looking for the first one, otherwise we want the second one. If we want the first one, then if c minus 0 is equal to first. And we use this. Same thing here, except we want the second character. So we brute force these two. We have the max length here. And now max length equals the mat.max of the max length and the length of these. Yeah, okay. That should be fine. 350 looks good. Check bounds, 1,000 test cases. We should be fine. So it'll take like half a second probably.
Well done, sir. AC on problem.
Got it. Segment intersections. You're given two lists of segments. I think I understand. Initially, all segments are equal to the first left to the first right. Okay, and all segments this are equal to the second left and the second right. One step, you can choose one segment from either the first or the second list and extend it by 1 in either direction. Let's define the total intersection as the sum of lengths of intersection of all corresponding pairs of segments. We take all pairs, find their intersection. Oh, intersection. Got it. Yes, I think I see. What is the minimum number of steps you need to make I greater or equal to k? All right. So we need our intersection to reach a certain amount. We could binary search that. Is it helpful to binary search it? Maybe. Let's consider that for a moment. Sum of lengths between corresponding. Oh, I see. So like this isn't just, that makes the problem easier, I think. So we're look at like the first segment from the left, first segment from the right, second segment from the left, second segment from the right. We have n different segments. And we want the total number of things to be at most k. So the number of steps could be quite big, so we have to be able to simulate the steps pretty fast. Yeah, who are the people solving this problem? Are they like wicked good, or are they just fast? Geothermal's fast and pretty good. Neil's very smart. Never heard of this guy. And Umnik is getting it wrong. No, Umnik got it right. Umnik, I think, qualifies as wicked good. Alright, so let's think for a bit. So, okay, we've got one segment here, and then we have n copies of them. When we want to extend a segment by 1, we pick any one segment, right? We pick any one of them and extend it by 1. So we have, if we do this, we'll have like 0 a bunch of times. So we have a bunch of zeros that we get as payoff. Eventually, our segments will look like this. Now we'll get a bunch of 1s as payoff. We'll get 1s up until this point. And then we'll still get a bunch of 1s because we can extend this. So we get a bunch of 1s here as well. Now after that, we have to extend this and we don't get any payoff, but then we can extend this one and we do get payoff. So then we have 0, 1, 0, 1, 0, 1. So this is kind of like the pattern that we get, which means we first greedily want to we want to take this part as much as possible. Okay, so if you've got some segments, there are a couple things that might happen. You might have this, you might have well, you might have this, you also might have this. Those are your three cases, I think. So this, you'll have like L1 and L2. L2. So it's just the, well, this is just, so you get like, this is like the distance between them. That's how big this is. Then this period of ones is going to be the union of the segments, the union of their length, minus the intersection of their length. So this thing right here minus this. Yeah, so leftmost to rightmost minus however much they intersect. That's how many times you get it for free. And then this is infinite. All of these are the same, so in total it looks like 0, 0, 0, then a bunch of ones, then a bunch of zeros. Oh, I see. This is easy to mess up. Yeah, then a bunch of ones. Okay, so you either want this or you want a bunch of zeros, then a bunch of ones, then a bunch of 0 ones. That doesn't, yeah, it's not really something that's too helpful, I'd say. Okay, so you want this, or you want like 0, 0, 0, 1, 1, 1, and 0, 1, 0, 1.
Always a pleasure hearing you work, sir.
We have company.
Understood, sir.
Okay. Good, but then we only have this only happens n times, and then we have 0, 1, 0, 1 after that. Okay, it's a bit messy. That's the solution idea. Oh man. Should we read calendar ambiguity? Is it just a race on time? What's up with the standings here? Yeah, you don't have time to do both, it looks like. So it looks like a bunch of people did D and a bunch of people are like, man, there are a lot of cases for D. I'm going to do E instead. Let's read it. Berlin year consists of this many months and this many days. Months are numbered from 1 to M. It also has a bunch of weeks. The first day of the year is also the first day of each week. Note that the last day of the week of the year might be shorter than W days. Okay. A pair XY is ambiguous if day X of month Y is the same day of the week as day Y of month X. Ah, I see. Count the number of ambiguous pairs up to a big number. This sounds much faster to code. So the months aren't, oh, the months are important. Yeah, this, I don't know. I think I'm going to do D instead. For now, at least. And then, apparently, F is also solved. Oh, D now. E has more solves now. Well, we'll do D first, and then we'll do E. How about that? It's a good compromise. Bicolored segments also has solves, but not by the top people. Looks like probably by speedrunners who are far down. Yeah. Oh, man. That's a bit... Well, that's fine. We'll just do D. Okay, so how do we do this? So we can either have this thing here, and then we can have that n times and then 0 ones. Yeah, this shouldn't be too bad to code, I don't think. So we are given L1 and R1, and then L2 and R2. Okay. Int n segments equals this. Int k equals this. K is the number of turns, right? Or k is the total. Target total equals this thing. L1 equals this, R1 equals this, L2 equals this, R2 equals this. So now int union equals, or int lmin equals math.min, L1, L2, Rmax equals math.max, R2, R1. Int union area equals Rmax minus lmin. Okay, so now we have this. We also want the intersection area. So int intersection area is R2 minus R1 plus L2, no, that's not right. R1 minus L1 plus R2 minus L2. So these are the sum of lengths. We want the sum of lengths minus the union area. So if, yeah, okay. So if this is negative, it's the distance. If it's positive, it's their actual intersection. So now int 0 or z prefix will be math.max of 0 in the intersection area, I think. And then int 1 length will be the union area minus the intersection area minus, well, math.max of 0 in the intersection area. Are we binary searching this or not? Okay, well, let's just try this. So way 1 will be a bunch of zeros, a bunch of ones, and then 0, 1, 0, 1. So long int equals 0 sys out the answer. So yeah, we need at least one required intersection. Ants equals z pre if target total is less than or equal to 1 length. Ants plus equals target total, else ants plus equals 1 length. And now ants plus equals 2 times target total minus 1 length. So this is really the first ants. Okay, we also want the ints 2. So how do we do this? Well, we yeah, okay. This is kind of an issue here. So we need to brute force the number of things to take. Yeah. That's why n is bounded by a small number. Makes sense now. So for int n to take equals 1, and to take is less than or equal to target, or is less than or equal to n segments, and to take plus plus. And now these ways are really the same thing. Long best ants equals long dot max value. Print the best answer. Just call this ants, and then at the end, best ants equals math dot min best answer and the current answer. So yeah, if we know we're gonna take this many, let's not do that. Oh wait, we have to do that. Okay, well that's fine. Alright, so the current left is going to be the target total. It's equals 0. Z pre times and take. Yeah, okay, so now if less than, let's make this a long, so we don't need to worry about multiplying. 1 length times n to take. If it's less than or equal to that, plus equals current left. Otherwise, plus equals this product. And then for left minus equals this product. And now 2 times cur left. Okay, I think all of this is fine, but it looks like samples aren't great, but they're good enough for me. Okay, let's look at what we're doing here. We have 3 segments in each group, an intersection of 5, they do this, right? That's the idea. I'm not even close. Okay. Oh wait, 3 test cases. So we just want 1 test case. It's this. Okay. The correct answer is 7. So let's print these. So the union is 3, the intersection is -1, 1 to 2, 3 to 4. That's right. The union is 4 minus 1. Okay. Yeah, so it's 0. Okay, so what does this actually look like? We got 0 for the first turn, then 1.
It's a pleasure hearing you work, sir.
1. We have company.
Understood, sir.
When we expand to both, and then a third one for the middle. Okay. And now we can have that we can have that up to 3 times. And then we get this. So the 1, 2, 3, 4, 5, 6, 7. This is the answer here. take, we got the answer plus this answer. So when we take 1, we get 7. 1, 2, 3, 4. Yes, then it takes 4 here. Should be 6, right? 1, 2, 3, 4. No, that should be 7. 4 plus 3. 1 shouldn't be 7. Z prefix is not 0. Z prefix is the that min of 0 in the intersection area. Negative intersection area. What? Last one. How is this 0? Wait a second. Oh, they already have intersection area. That's wild. Okay. Yeah. So target total. Oh, that's weird. This needs to be a long then. This also needs to be a long. Okay. This long, this long. Okay, so now target total equals math dot, well, okay, so if intersection area is greater than 0, then target total minus equals the number of segments times the intersection area. If target total is less than or equal to 0, this out 0. Continue. Got it. So I think that's fine. All right, so now I don't think any of this is important anymore. Okay, I think that's fine. But I see how lots of people could easily get this wrong.
Well done, sir. AC on
All right.
problem D.
It's good to hear. How are people looking? We've got E and F in a reasonable order. So let's do, yeah, let's do the math for E, I think. I think that's the play. You've got M months with D days each. Months are numbered 1 to M. Yeah, the week has this many days. Well, actually, I'm gonna go to the bathroom. I'll be right back. got months, days, and weeks. You want the weekday to be the same, the month days to be different. Yeah, you're picking some day. 2 different days that are the same. Oh man, this is like kind of hard to wrap my head around. Oh. Okay, so we want the same, no, what do we want? The same day of week. And then we want day 1, or like day of month of the first thing equals the month of the second thing. And the month of the first thing equals the day of the month of the second. So both of these need to be like less than or equal to the min of the number of months, and also the number of days in each month. Because one of these numbers needs to be a month, the other needs to be a day of the month, right? So we only care about the minimum of those two. So this is equal to the value mod the month length, right? Okay, so val mod, or I guess let's call this x, because x can be the first time, right? So we know x mod the week length equals y mod the week length. Then we want x mod the month length to be equal to y over the month length. And then we want x divided by the month length to be equal to y mod the month length. In days. Everything is big, so we can't iterate over anything itself. I hope the way people are solving this isn't they just look for patterns. Alright, sorry about that. Okay. Well, let's try and actually solve this then. We want to find the number of solutions to this problem. So let's say we knew x. Let's imagine we knew x. So let's say we brute force x. We won't actually wind up doing this, but it might be helpful to get some insights. So now if we know x, then we have x to a y plus like n weak lengths. Yeah, so y is equal to x plus some number of weak lengths. So we know what month y needs to be in. Oh, maybe this is like a square root thing. Wait a minute, hold on a minute. Could this be a square root thing? If the weak length is small, oof, square root ideas flying everywhere. If the weak length is small, we can brute force x's value mod the weak length. What if the weak length is big? I guess we could brute force what this is. I don't know that this will be particularly helpful. And we can always either brute force x. We can always either brute force the month or the day of the month. One of those will be small. Interesting. So maybe we need to brute force the month, and then later on we'll need to brute force the day of the month. Okay, so if we know the month, how does that help us? Well, it's not really, because the two things aren't in the same month. So it's really the X month that we know. That's it. The Y month can be anything still. Yeah, this is like pretty unhelpful. Let's look at the examples that they provide. So month 1, day 3 is the same as month 3, day 1. Week 2, or month 1, day 5 is month 5, day 1. A given day can only work at most once, so the answer is at most 10 to the 18. Or the answer is at most the number of days total, even. No, the answer is at most 10 to the 18. There can be 10 to the 18 days total. Well, this contest got hard fast. We'll try reading this. You're given n segments. Each segment has one of two colors. The I segment color is this. Let's pair segments I and J, or let's call a pair bad if they're different and the segments intersect. Yeah, calculate the number. Wait. Does the color even matter? Calculate the maximum number of segments that can be selected from the given one such that there is no bad pair. Oh, the colors are different. Yeah. Is this just segment tree flow? I like this problem more than I like E. My issue with E is I just might never be able to solve it. But I think I can get problem F. If we want the maximum matching in a bipartite graph, because we have a bipartite graph, right? We've got segments of one color, segments of the other color. We want the maximum matching. The maximum matching is just the number. You can pick everything minus the min cut. So it's the number of segments in total minus the max flow of that graph. So you could do a bipartite graph with n log n edges and then run flow on that. That would work with all unit flow. Yeah, kind of. You're kind of doing that. Because you need, like, yeah, you've got a continuous range of elements. Maybe, let's think about F for a minute. So you've got something like this. You've got like this here. So you've got a bunch of, here are all of your segments. And then you have your implicit segment tree. Now you have some segments over here. And now these go to the deepest that they can handle, maybe. These things flow like this. We care if there's any intersection between them. So you can do it n root n edges for sure. Then flow on that. That's a bit tricky. It's also not general flow because this isn't a general graph. A general bipartite graph at least. Maybe that makes it easier. Maybe you don't actually need flow for that. But understanding how flow works would definitely help you solve the problem. Oh, I see. We can divide this into, we don't need a segment tree here. Or well, we can divide these into order n segments, right? If we divide these into like a bunch of segments, then here are all of the relevant pieces. So then we will have another layer of our graph that handles those. We'll have something like this, right? And that handles like this layer of abstraction. So stuff is going on here, but really it just like that's handling all the edges in a fast way. And then we need to do a range connect. So that will be, if we do a range connect, that'll be just add log n segment tree edges. Yeah. So you do a range connect with segment tree edges. So you would have order n nodes, but n log n edges. Which might be not good enough. It's hard to tell. It's v root e, right? Or e root v. That's an idea. I'd like to be able to see how much time that took. Maybe it's not flow at all. Maybe I'm just going down the wrong path. Well, I should be able to solve E though. Scoreboard says E is easy. Or not impossible at least. Yeah, if it's got 100 solves, I should be able to do it. So let's dig in on E instead. Alright, so we want the same day of the week for both of these things. In addition to the same day of the week, it's got to be this day. It's got to be this day of the first month. And then this month. If you pick 2 months, do they work, I guess, is the question. Or if you pick 1 month, can 2 days be the same? Day of the week. Yeah, what happens if you pick 1 month? So if you have some month here, you've got a bunch of days. Wait, are there a whole number of, there aren't a whole number of weeks per month. So now the question is, we can pick any day. Which day corresponds to a month that's the same as us? Which days, I guess, would be the same day of the week? As like this month as a day would be. Man, that's not easy to calculate though. Okay, I don't like that. Let's not think down that path then. So what if we brute force the day of month? Or the day of week? So now we don't care about this requirement. Now the question is, how many of this day of week is this day of the month. Yeah, okay, so like how many well, what will this look like? So if we brute force the day of the week, we'll have like one. Maybe we should do this example here. So let's do the first day of the week. So we have 1-1. I'm gonna move this just over here so it's easier to copy. We'll have 1-1. This is the month, and then this is the day. Then 1-5. Then 2-2. Month 2, day 6. Month 3, day 3. Month 3, day 7. Month 4, day 4. Do these have to be not the same day? Yeah, okay, they can't be the same, it looks like. Month 4, day 4. Month 5, day 1. Month 5, day 5. 2, 3, 4, 5, 6. Month 6, day 2, and month 6, day 6. Okay, so this won't count, this won't count, this won't count, this won't count, this also won't count. Because 1-1 is the same day as itself, right? That's all we're saying. So somehow we need to eliminate. It's interesting these all occur on the first day of the week. 1-1, 2-2, 3-3, 4-4, 5-5, 6-6. I guess that's not interesting at all. Yeah, that's not interesting. But we can remove these at the end because there are just, that's easy to calculate how many of these there are. So now we want to say how many 1-5s are also here. How many 2-6s are also here. How many 3-7s are also here. Not enough. Why? Well, 3-7 doesn't work because there aren't 7 months, but there would be. If there were 7 months, it would work. So why is it that these both have pairs? That seems very coincidental. Seems very special. Everything works? Why does everything work? Like everything that could plausibly line up ends up lining up. Why would that be? What am I saying here? I'm saying if you count, so this is going to be 1 times the month length plus 5, or, well, okay, it's 0 times the month length plus 5. Plus 4 is equal to 4 times the month length plus 0. When I say equal to, do I mean exactly equal to? Or do I mean equal to mod the day of the week? Mod weekday, or mod week length, yeah. this always true? When is this true, I guess? Is this only true when the month length mod the length of the week is 1? Is that even true here? Well, this is equal to 3. The month length is 3. Yeah, mod the day of the week is 3. So 0 times 3 plus 4 is equal to 4. Maybe I don't have enough. Okay, yeah, so it never occurs. It occurs twice in the beginning, twice in the end. That's odd that it is like that. Maybe patterns are pretty important. $47 minutes left. Feels like some nonsense because this occurs, like the number of pair things occurs in 2 different days of the week. And if we take, yikes, okay. If we take the GCD of these, that's 2. So that could be where the 2 comes from. What would that mean? M is the number of months in a year. W is the number of weeks in a year. No, W's the number of days in a week. Would there be any relationship between the number of months in a year and days in a week? One, choose, well, we don't have 1, 3, I guess, right? There's no 1, 3. Why not? Because it doesn't occur on the right day of the week, of course. So maybe the better idea is to look at all pairs and see which pairs work. Does, so, well, there is 1, 3. So I guess what pairs work? 1, 3 works. 1, 2 does not work. Why does 1, 2 not work? It's 2's in the wrong column. All right, 1, 5 works. Wait, they're saying 1, 5 doesn't. Oh, 1, 5 does work. 1, 7. How about 1, 7? Well, nothing works with 7 because there aren't 7 months. Okay, so the numbers are actually 1. Hello? The numbers are 1, 3, 5, and 7. Well, no, they're 1, 2, 3, 4, 5, 6. Those are the numbers that we've got. So 1, 2 doesn't work. 1, 3 works. 1, 5 works. 3, 5 works. 2, 3 doesn't work. Wait. 2, oh, because 2 and 3 occur in different things. Okay, so this splits it into two groups, but 2, 4 also works, maybe? Yeah, 2, 4 also works. Two and 3 are always different days of the week, it looks like. Wait, that's not true. So why do we have these two groups? Wait, what about 4, 2, 6 also works? Does 4, 6 work? 4, 6 also works. So what is special? Why are there these two sets here that are interesting? Where does that come from? I'm not seeing the math. A 2 comes from somewhere. These are coprime. I'm worried there will be a bunch more patterns when it's not coprime, so just finding the patterns might not be sufficient. This is important at least though. So why does 2 and 3 not work, I guess is the golden question. So 3, 2. 3 and 2. So we care about the second month, day 3. And then the third month, day 2. Second month, day 3. It's a different day of the week than the third month, day 2. Maybe we look at that. So the days in a month, D is days in a month, right? Yeah, number of days in a month times 2, or times 1 really. Plus 2 is not equal to the number of days in a month times 2 plus 1. Seven, well, modulo, we're doing this all mod 4. So 7 times 1 plus 2 is not equal to 7 times 2 plus 1. So this 7 is really 3. So we're saying 5 is not equal to 7. Yeah, that's true. So why do 1 and 3 work? So D times A plus B. Does this equal D times B plus A? So if we subtract 1 from both sides maybe, then we have D times or d minus 1 times a. Does this equal d minus 1 times b? Modulo the weekday, days of the week. Well, this is hard to tell. We can't divide, right? Well, we're multiplying a and b by the same number. Yeah, so when are a and b the same number? If we multiply them by the same number, doesn't matter. What is d? What is d in this example? D is the number of days in a month. Days in a month. So that's the question. Then everything that's like this, all of these things are in the same group. Which means all pairs will work. Will all groups be the same size? Man, this is probably a math thing that a bunch of people already know, but I have to figure out live in contest because I am not good at math yet. If you take, well, like, if this were a prime mod, this were prime, these would never be equal. These would only be equal if a and b were the same. Does the days in the month even matter? Yeah, it matters. Should we write a brute forcer? Days in the month. Why is days in the month important? Because we're multiplying it by this. When do two things become equal under mod? They are equal under mod. Yeah, okay. So you're equal under mod if you're equal under all prime factors. That's the only time you're equal. You're only equal under all prime factors if either you're the same or all the prime factors you're different from are divided out by this. That's why this is important. Okay. Yeah. So the GCD of the days and month comma the week. These are the prime factors that don't matter. Is that true? Days in month minus 1 even though, right? Yeah, days in month minus 1 in the week. So I never would have gotten this from the pattern. I was looking at the 6 and the 4, but the 6 and the 4 have nothing to do with it. It's the 7 minus 1 and the 4. So this GCD these are all factors which don't matter, right? Like these are shared, so these factors don't matter. Which means we can have as many of these as we would like. So if we have some number like, yeah, we want to figure out the size of each group, right? That's the idea. So if we know the number of things in each group, well, the number of things in each group is at most this GCD. So we're interested in factors of this GCD now. Yeah, all right, I have to go to the bathroom again. So like if we know how many things are in this group, man, please, my phone. If we know how many things are in each group, it's just that choose 2 times like the number of, like it's that choose 2 summed over the number of groups. So maybe we look at this here. Yeah, summed up to 10. So we can include numbers up to 10. Well, like, let's see. So numbers up to, the number of months is 10 months. And then the number of days in a month is 7. So up to like, we've got pairs 0 to 6, assuming we do 0-based stuff. So now, for what pairs are the number of days in a week? So are 11 or days in a month is what's important. So days in a, so this is all, we're doing this all modulo days in a week, which is 12. Okay, we're doing it mod 12. Now, we care about the number of days in a month is this number here. So 6 times A, when does this equal 6 times B? Modulo 12. So the 3 doesn't matter. So we care about 3 doesn't matter. So really, when does 2 times A equal 2 times B? modulo 4. So what are the values of 2 times a? Either it has a factor of 2, well, up to 7, right? So it's 0, 1, 2, 3, 4, 5, 6. So 2 times a, 2 times 0 is 0. 2 times 1 is 2. 2 times 2, yeah, so we can get rid of this 2 as well, I think, and just make this a 2. So it's just values mod 2. So 0, 1, 0, 1, 0, 1, 0. So this occurs 4 times, so it would be 4 times 3 over 2 plus 3 times 2 over 2, which is 6 plus 3, which is 9. That's the right answer. Okay, so we're on the right track here. So this is just, yeah, okay, this is just a math problem. But, you know, if you're going to be good at competitive programming, sometimes you just have to suck it up and do math, even though it might not be fun. Yeah, so I think we're on the right trail here. We're very close. How much time do we have left? All right, so I think the plan is just like strategize to make sure we get this problem, because even if I get it like now, I probably don't have time to do F. So just try and get this and then minimize stupid wrong submits. That's my plan at the moment. So we can, since we can divide out, yeah, so this is just, this number here is the like count up to. And now we have a certain number of things that are all zeros. Yeah, okay, now this mod here is going to be, yeah, like divide out the number of days in a week minus 1, is that it? Or where does the 6 come from? The 6 is the 7 minus 1. So divide out GCD of D minus 1 and the actual mod, which is W. And that's our actual mod. So we get our real mod. Now we just have a bunch of things that are like a bunch of, like we have a bunch of things that occur 4 times and also a bunch of things that occur 3 times. Yeah. Okay. I think that's not actually too bad. Static long and choose 2 and turn this needs to be a long, turn n times n minus 1 over 2. N equals this, D equals this, W equals this. Okay, so let's make these longs. Long, what did I call this? The count up to. That's going to be the minimum of the number of days in a month and the number of months in a year. Okay. So now, long mod, we're going to GCD. Okay, so now, yeah, long real mod equals the W divided by GCD of W and D minus 1. Okay, so now we have this real mod. Okay. So this is the mod of these numbers here, the mod that things cycle by. And we want to count things up to this number. So long and smaller will be, this is the number of smaller groups, will be count up to modulo the real mod. Long smaller size will be count up to, will be, yeah, count, well no, it'll be the real, no, count up to divided by the real mod. So this is the n bigger, really. Yeah, okay. So now long n smaller will be just real mod minus n bigger. So our answer will be n choose 2 for the smaller size times the number of smaller things, plus n choose 2 for the bigger size times the number of bigger things. Or this is bigger size is just n smaller plus 1. And that's our answer. Oh no, do we print it under mod? Wait, I got this wrong. Okay, this out. Real mod is this. So what is our real mod? It should be 6. Real mod is 2. Yeah, that's right. Count up to maybe count up to. I'm like not even close here. Let's get this case. Count up to is 7. Yeah, okay. The real mod is 2. Yeah, that's right. It should be one of each, right? One of each. We shouldn't be getting this wrong. Smaller size is 3. We literally just did this math. It's 4 times 3 over 2. N times n minus 1 over 2 times 1 plus 3 times 2 over 2 times 1. Oh wait, this is not n smaller. This is smaller size plus 1 over 2. Yes. Thank you. Okay. How many test cases? Not many, so we should be able to submit this and be fine. Well, let me make sure I get it correct before we're talking about it. Okay.
Well done, sir. AC on problem.
So as easy as of a problem as that should have been, 1, it took me an hour, and 2, that was like on the verge of the level of math that I'm comfortable like actually solving in contest. So yeah, 400 people are solving it. That shows how bad I am at math, man. Like, I don't know. It wasn't hard. It was just like an equation, but I really struggled. Maybe I just need to be better at math. I don't know how other people get that so fast, to be honest. I didn't see it. Okay, well, we've got 18 minutes. Let's try and solve F. And if we can't, that's not the end of the world. How is geothermal winning? How's he doing? He's in 4th place. That's quite good. Nice job. Omnic solved set. Expected nothing less of him. William Lin got problem F pretty quick. He also is a math ninja, so that would explain quite a bit. And Monaghan's doing all right as well. Always good to see. Back to problem F. Yeah, we could do segment tree flow. I'd be concerned about runtime though. It's my biggest thing. Yeah, that's my concern. Let's try it. So single test case. And then the number of segments. Yeah. We need to pick the number of points so that no two intersect. So all that's relevant is the coordinates. They're inclusive. We probably want to make them inclusive. Can they intersect at a point? They can. Yeah. So make inclusive, exclusive. Or we can just do inclusive and coordinate compress. So we'll have our seg. Well, we should probably just make them all in one group, right? Yeah, okay. Color. Is that color equals color? Yeah, alright, so now seg array segs gives me seg array and segs for diagonal 0 less than segs plus segs at I equals seg. Those things. Yeah. Now int n ones equals 0 for seg s. Well, let's just compress now. Static void compress seg array segs hash set, or I guess tree set integer x's so tree set segs, x's.add, s.l uncompressed. So at the right uncompressed point, and now for for int I, this is hash map integer compressed new hash map compress dot put I to compress dot size for seg s and segs s.l equals compressed at get the uncompressed left. Same thing with the right. Good. Do you have to print the answer? No. Okay, so now max ants equals compress get size minus 1. Max endpoint. Okay, now we need a segment tree. Static class seg tree. Leftmost, rightmost, and also ID. Static int global ID equals 0. Seg tree child public seg tree. If leftmost not equal to rightmost, then mid equals new seg tree from the leftmost to the mid. Our child equals new seg tree from the mid to the rightmost. Okay, so now we have this. Good. So we compress these segments. Int n on left well equals, or we don't even need to do this, right? We can just iterate through each segment. Yeah. Well, we might actually finish this, interestingly. Didn't expect to, but it's possible. So we need our Linux code here. Come on, we're not going to use bit sets, no one cares. Thank you. All right, so we want, yeah, okay. So now, Dinic, it's got to be static, right? Static, Dinic equals new Dinic. We can't make it yet. Equals new Dinic. How big is this graph going to be? Well, the number of segments plus the source and the sink, those are included, plus n log n, right? Or plus times the max things times 2. Max end point times 4, I think. It takes n minus 2 to represent, there's a power of 2, so this should be enough. Yeah, okay. Oh, we can just build the seg tree first. Seg tree st will do seg tree from 0 to max endpoint minus 1. Nope. Let's just do this. Okay, 0 to max endpoint minus 1. So now and segs plus gid or segtree.gid. Okay, so we have our DINX. Now for seg s and segs, if s dot color is equal to 1, then on the left, so now d dot add edge from d dot source to all of these things. Okay, this is the tricky part. Oh no, to yeah, this doesn't work. Let's put the global IDs first to make things easier. So add from the source to the segtree.gid plus I. You can choose this once, the initial flow is 0. Otherwise, it'll be color 2, in which case we go from this, or we go from this node connecting to the sink. Flow is 1, let's do 0. Okay. Now add to segtree. Okay, so public void add int from index, well int seg other index, and then boolean forward. Okay. So in this case, we want to do st.add from segtree.gid plus I, true. We also need the left and the right, s.l to s.right. And this is just the same thing, except it's false. If L is less than or equal to leftmost and R is greater than or equal to rightmost, then add it. Else if, well, turn the left endpoint is greater than the rightmost endpoint of the range, or the right endpoint of the range is, or the right endpoint of the query is less than the leftmost endpoint of the range, then just return. We don't care. Otherwise, lchild dot add, same thing, and rchild dot add the same thing. All right, how do we add this to our DINIC? So if forward, we do one thing. Otherwise, we want to add the reverse edge. So now d dot add from the other index to ID, capacity 1, flow 0. Otherwise, add the reverse from ID to other edge, other index. Okay. And now in flow, it goes via flow. This out, well, okay, the ants will be the number of segs minus the flow. Nope, print the answer. How crazy would it be if this works and we got the problem? Pretty crazy, that's how crazy it would be. No. Okay, I think that's fine. If L is less than or equal to leftmost and R is greater than or equal to rightmost. And add an edge to me. Capacity 1, flow 0. Otherwise, add an edge from me to him. Flow is 0. Why would the flow be 0? Let's do I guess print for each seg. Why can't we pick these two because they intersect? Oh, yeah. Okay, so you can add edges to between the trees. Yeah, okay. Public void. Well, when we do this, we can just do public void precomp. lchild.precomp, rchild.precomp. Okay, and now we also want to do d.add edge from id to lchild.id, d.infinity flow 0, child id. Flow 0, what? Oh, we also need to add it back. Oh, we don't call precomp. T.precomp. Okay. Oh, darn. Wrong. Man. What am I saying the flow is? Am I saying the flow is too big or too small? I'm saying the flow is 2. Well, darn, I'm so close. Yeah, I wonder if this is segment tree flows intended. Can I see some of my friends? What a clutch, man. Emma did what I couldn't. Nice job, Emma from UBC. Come on, get me. I guess I can't see him. Well, it's fine. Alright, solution time. Very good. Problem A. So problem A was, I guess, a good problem A, I thought. So you're given, in the problem A, you're given 2 integers, which are like a lower bound and an upper bound. and you need to find some pair of integers between them where the integers are both between that range and they're different, and also the LCM of the two integers is between the range. So if you want like the LCM to be between the range, like if you've got, let's say you have like, let's say you've got the numbers like 2 and 3, right? So you've got 2, you've got 3, and then you need the LCM of 2 and 3 to be all within like some range. So this is your L, this is your Y, or your R. So if this is what you're looking for, then there's no reason for this 3 to not be the LCM. Like, it's perfectly okay for you to just pick what the LCM is, and then say, I need to pick this number and a factor of this number. And that's the idea. So if we pick this here, we know this has to be slightly different from it. We can just make it like, this is the smallest number here. So this is like, we can just make this L. We can make this 2 be L. And now if this is L, that's like as small as it can get. And now if we have L times 2, this is the smallest thing you can get by adding some factor to it. Since you know the two numbers are going to be different, the second number has to be at least one factor bigger. This is the smallest number that's one factor bigger than L. So the LCM has to be at least this big. We found a way of making it this big. That means this is the smallest R that you would at least need in order for there to be any answer in the range. So if this works, then you have a working answer. If this doesn't work, you know there are no working answers. So you just try L and L times 2. Either that works or it doesn't. You just print that. Okay, very cool. Array walk. This one, man, I don't know. I did a DP, so maybe you don't need a DP, but I thought it was a bit harder than problem Bs usually are. That's fine, I guess. So the idea would be, okay, let me erase this so that, actually I need that to explain it later. Otherwise I might forget. So you've got like some position in the array, and on a given turn you can either walk right, you can also walk left, and every time you walk to a new space you get the score excuse me, you get a score based on the value of that space. So yeah, it might seem like a pretty easy DP. You get to take at most k steps. So now, instinctually, if this were the entire problem, then we would have like an n times k DP. Because what matters is what position we're at and how many steps we have left. But there's this additional constraint, which is you can take at most z left steps. And when you have this, that makes things easier, because then if we store k in the z that we have left, we can figure out where we are. So k is the number of steps we've taken. We've taken z of those going left. That means the number of right steps that we've taken is k minus z. So if we know how many right steps and how many left steps we've taken, we no longer need to store what position we're at in our state. So let me draw an example out, because if this is new to you, that might be a bit confusing. So let's say we know we've taken 5 steps. Let's say taken 4 steps. And also we've stepped left once. That means we've taken 3 right steps and 1 left step. So that means our position would be, we start here, we go right 1, 2, 3 times, then we go left once. So this is currently the position we're at, which means we don't actually need to store what our position is in our state of our DP, because given just these things, that's enough information to figure out what subproblem we have left to solve. That's the idea. So yeah, so basically you just do a DP, and you do a DP where your state is like how many steps you've taken so far and how many like left steps you've taken, and then also whether your last step was going left or not. So this is just size 2. and this is equal to the maximum score you can get. You have a transition of 2, so you can always step right if you have more things to do. You can step left as long as you have like things left to spend here. So the last left isn't 1, and also you have Z left moves left to spend as well. So if you have any moves you can spend to walk left, and you didn't step left last turn, you can step left now. An implementation trick that I think is kind of helpful is if you do this recursively, if you write your DP recursively, you can actually store how many moves you have left in your DP, but just not memoize it. And the nice part about this is like, it looks like this is a n times k times z times 2 DP, but really this thing is predetermined by the rest of these. I'm just passing it into my DP so I don't have to worry about doing math in order to recalculate it at each step. So like, I think that makes it a little bit easier to implement, in my experience at least. And yeah, other than that, it's just a pretty simple DP. So the idea is that first I fill in my DP with -1s, then the answer is just DP it. You can take this many steps, you haven't stepped left in the first turn, and then you didn't step left last turn. And I just here are the conditions that need to be satisfied in order for me to be able to move left. You can always move right, and then I just keep whichever one's best. All right, so that's problem B. It's possible there's an easier solution, but my guess is that that's the intended, having not seen the editorial because it's not out yet. But yeah, that's problem B. Let's look at problem C. It was a little bit harder than usual. C was harder, or B was harder than usual, I thought. In fact, it had fewer solves than C, which is understandable. Okay, problem C. So you have this cyclic, you have this string. Maybe your string is like A, B, or it's digits, right? Yeah, it's all digits. So it's like 0, 1, 0, 0, 1, 0, 1, maybe. And what you want to do is you're going to remove some digits from the string, and then you want to make it so that if you cyclic shift the string once to the right, that's the same as cyclic shifting it once to the left. We can do a similar analogy. So first, let's cyclic shift it once to the left, right? So now, after we do this, if we move this over here, then we have 1, 0, 1, 0, 0, 1, 0, 1. So let's just do that once and now solve it on this problem. If we're solving the same problem here, now the version of the problem that we have is we've got this, and then this shifted by 2. Which means if everything gets shifted by 2, you have these requirements like this. So let me draw it differently. These need to be the same. These positions need to be the same. These positions need to be the same. And then also these red positions need to be the same. So if it's an even length, you have these two groups, and then this cycles around to this here, and this green one cycles around to this one here. So if it's an even length, if the string you end up with is even length, that means every other position needs to be the same. If it's odd length, then you have something like this. So let's do like that. Then you have these first two need to be the same. The next two need to be the same. This needs to be the same as this one here, right? Because these are like related. And then these need to be the same. So really, this is all, like everything needs to be the same number. And we've reduced it to this problem, like it's easier to think about, because instead of modifying this in two ways, we can just modify it in the first way, and then shift it twice in order to look at what the second way would be. So, all right, cool. So now we've got this subproblem. We need to delete letters in order to either make it so that like the first character is the same as the third, and the fifth, and the sixth, and then the 0 character is the same as the second, and the fourth, and the sixth, or whatever. Like every other character needs to match with the 1 and 2 before it. So we need to either turn it into that if it's even length, or an odd length string in which everything is the same. So this odd length string is really easy to handle. If we just store the frequency of every digit, then we just take the most frequent digit, and that's our answer for that. If it isn't this odd string, which happens in samples, like this sample right here is really good, super helpful, I think. In this case, what you want is you're going to be alternating between like one digit and then another digit. So you can brute force what those are. You brute force D1 and D2. And now you want to find the longest common substring between D1, D2, D1, D2, D1, D2. Or I guess like the longest common subsequence in this that matches this. So what you can do is you just you check this first character, and then you have the pointer in where in this string you are, and you want to find the next thing that matches D1. So you just march through this top string here, and every time you find a D1, then you increment this pointer. Now if you find a D2, you increment the pointer. Same thing if you find a D1 again, and then you keep going. You can do this, like this string is infinitely long, so it doesn't matter. But then you have to keep track of which character you end at. And if you end at D1, we're ignoring the requirement right now that this string has to be of even length. So if you end at the first character, you have to subtract one from your candidate answer. So since we're brute forcing what D1 and D2 are, no matter what they should be, we can find what the best answer is by checking all possible pairs of D1 and D2. So then our final runtime will be 10, because there are 10 digits, 10 squared times n. And that is like roughly, I think, 3 times 10 to the 7, 2 times 10 to the 7. So that's fast enough. You can do about 10 to the 8th things per second in Java, and there's a 2-second time limit, so that should be fine. Also, it's like super low overhead, so it's probably much faster even than that. Yeah, it took 0.2 seconds, which I guess is exactly as long as you would predict from the runtime. 2 times 10 to the 7 is 1/10 of 2 times 10 to the 8, so it should take 1/10 of 2 seconds, which is what happened. So yeah, that's the idea behind problem C. Let's look at problem D. So in problem D, what was problem D again? Yeah, segment intersections. So this one, you had to be kind of careful because there were lots of ways in which it could go wrong, I think. But it wound up being a pretty nice problem in my opinion. So you've got some segments, and on a given turn, like you have a bunch of segments in this pile, they all look like this, and a bunch of segments that look like this. On a given turn, what you do is you pick any segment that you want, and you extend it by 1 on one of its sides. So I guess that doesn't really look good. Like, we've extended that segment now. The next turn, maybe you take this segment and you extend this one. And then what you're going to do is you want to look at these first, this segment here and this segment here. You want to take their area or their like intersection length, and you add that to your total. And now you do the same thing. You add this length with this length to your total, and then this length with this length to your total. Now, right now, none of them intersect. So the answer would be 0 for the moment. But you can imagine that if we move these so that they're easier to look at, like that maybe. It's still kind of rotated, but that's fine. So maybe on the first turn we move this one like that, then the next turn we add one like that. Now we have an intersection area of 1. Now we can keep adding and keep getting an intersection area of 1. So we got +1 for all of these steps. Once we have this, we can add to this bottom one here and get a bunch more +1s, because these pairs intersect. Yeah, okay. So now once we have that, if we want to keep adding to this pair, what we can do is we can add 1 to like the top, and then also add 1 to the bottom. So let's look at the amount the intersection increases each time we add one of these extra spaces. So initially, we have, like, initially before we started adding any of these, we got +0, because we have to reach across until we reach the other group. So we get +0. We might get +0 for a while. And then the number of these +0s is going to be the distance between these two. Now for this top pair, we also get a bunch of +1s, and we get these for a while, corresponding to, you get to cover this middle, so you get these points here, You also get points for covering one of these segments. You also get points for covering the other one. So you get a bunch of plus ones. And then after getting all of these plus ones, you have to like extend the top and then extend the bottom. So then you get a plus 0, plus 1, plus 0, plus 1. So like after you've got this, you got like plus 0, plus 1 forever. So you've got these three groups of things. Now, keep in mind that this initial, you get a bunch of zeros, then you get a bunch of ones, this benefit. You can get this thing multiple times if you have multiple segments. So we can do this up to like, we can do this one time, we can do it 2 times, we can do it all the way up to n different times. So since the number of segments in total is guaranteed to be pretty small, we can brute force the number of times we do this. And then on top of that, after we have done this a bunch of times, then it's just this 0 and 1 part that's left over. So yeah, that's the idea. We brute force the number of times we have these groups of zeros and ones, and then after that we have all 0, 1, 0, 1, 0, 1 alternating. And this is just 2 times the number of ones left, which is pretty easy to calculate. So the last thing I want to talk about with this problem is the implementation details of how do you actually go about oh, I see. I figure out when my F is broken now. So I know how to fix it, I think. But anyway. Yeah, so the question is, how do you actually calculate the length of the 0 group and the 1 group? And you can do that by like looking at things kind of carefully. So we can, like, if you've got these 2 segments here, I calculate this length here from like the leftmost of both of their left endpoints and the rightmost of both of their right endpoints. And now on top of this, you also know the sum of their lengths. So you know this blue part plus this blue part. You can figure out how much they intersect by it's just blue minus green. Will just be the intersection area. This can be negative if they don't intersect. If it's negative, it's this distance here. So that's a very clean way of getting this distance. It's just the blue minus the green. And then the green is just the maximum of the right endpoints, the minimum of the left endpoints. The blue is just R1 minus L1, R2 minus L2. Then you add those up. So you can get all of these things. So now, if we want the number of zeros, that's just this here. This is like the number of zeros. Then the number of ones, like let's call this A, this B, and this C. The number of ones, well, I guess let's not do that. Sorry. The number of ones will just be the total green amount minus the intersection area. Now this might be negative if you just use it by default, so you want to max that with 0. So that will handle the case where you have lines that look like this. And you want to avoid counting ones here because you can't like extend either segment into this line. So now, once you've got this, we have company.
Understood, sir.
Sorry, that's my bot. So, yeah, once you've got the length of the zeros, the length of the ones, then you can just calculate this formula. You're brute forcing the number of line segments you care about. After that, it's just like times 2. So that should be pretty easy. You just got to be careful not to get the math wrong. So yeah, there's my code. I think I explained what all of it does, so it should be pretty straightforward. Let's look at problem F, or problem E first, and then problem F maybe. Yeah, okay. So Berlin consists of several months with several days. Yeah. So for this problem, what you're looking for, like what the ultimate question is how many pairs of days are there, x comma y, where the xth day of the yth month is the same as the yth day of the x month in terms of days of the week. So if we have some week length, we want x mod week length to equal y mod week length. We also want x mod the month length to equal y divided by the month length, and x divided by the month length to equal y mod the month length. So this is what we're looking for. So what you can do on top of this is we can say what pairs actually work. And let's look at this. So in the sample, 1 and 3 work. Namely, you can have 1, 3, and 3, 1. That works out nicely. So the reason that it works, like we'll consider all pairs, and let's consider the ones that are the same day of the week. So this D is the number of days in a month. So we're looking at, or this is, I guess this is 2, 3. Rather, this math is for 2, 3. So the question is, why do 2 and 3 not line up? Well, 2, we've skipped 1 month. There's 1 month before 2. So the number of days in 2, 3, the number of days before that, will be the number of days in a month times the 1 month that comes before 2, plus the number of days that comes before the 3. So then, like the effective index of that day will be the number of days in a month times 1 plus 2. And we want to evaluate this mod 4. Now, we also want to evaluate the number of days of the 3rd month and the 2nd day of that month. So it's the number of days in a month times 2 plus 1 for it being the 2nd day. This is like the number of days in a month in the sample is 7, but we only care about its value mod 4 because we only care what day of the week it is. So 7 mod 4 is 3. So if we actually evaluate this, this is saying this is equal to 5 mod 4, which is equal to 1. And this is equal to 7 mod 4, which is equal to 3. So these are 2 different values. That means that they're going to occur on different days of the week. Okay, so we've seen that one example. But in general, they'll occur on the same day of the week. A comma B will occur on the same day as BA. If D times A plus B is equal to D times B plus A, where D here is the number of days in a month minus 1. No, it's just the number of days in a month. Yeah, not the minus 1 part. Okay. So we can do some math to rearrange this equation. If we subtract A from both sides, then we'll have D plus A minus A. And then on the left side, we'll have D times B minus B. And then we can like factor out the D, or factor out the A, I guess. So now we have D minus 1 times A, and then D minus 1 times B. So we want to see when are these two the same. For what pairs of A and B are D minus 1 times A the same as D minus 1 times B? Now, basically, if our week was prime, right, if the thing we're modding by was prime, then this would never actually happen because we could divide this number out from both groups. But we can't divide it out because it might not have a mod inverse under this mod. Now that's a bit complicated. I made a video on like how to kind of understand mod inverses for prime mods, but when you don't have a prime mod, then it's a bit tricky to like comprehend that, mainly because sometimes a mod inverse doesn't even exist. So we can't like safely divide this number out from both sides of the equation to see that A is equal to B only when A equals B. There might be other times that it's equal. So what we can notice is like if these share a factor, if this thing we're multiplying shares a factor with this, like, okay, let's slow down for a minute. So 2 numbers under mod are going to be the same only if they're the same modulo all prime factors of that mod. So you have to be like, if let's look at some 2 numbers mod 6, right? So 5 mod 6 and 3 mod 6. we care about these numbers modulo 2 and modulo 3. So 5 mod 2 will be 1, and 5 mod 3 will be 2. 3 mod 2, let's do a better example than that. Let's do, well, no, that's fine. So 3 mod 2 is 1, but 3 mod 3 is 0. So since these aren't the same, that means that like under whatever mod that we're trying to find, they won't be the same as well. Because these are different. So yeah, we want these pairs to like be the same. That will mean they correspond to the same number under the big mod. Now, how do we apply that to this case? Well, we might be multiplying in some factor of 3, for instance. If we multiply in that factor of 3, we no longer actually care about what this thing's value is under mod of 3. We only care about its value mod all of the other prime factors. Because it'll be equal to 0 mod 3 since we're multiplying it by 3, or some multiple of 3. That's true for anything else too. If we multiply it by 2, we don't care about what its value is for a factor of 2 if w only has one factor of 2, right? That doesn't matter anymore because we know it'll be equal to 0 since we're multiplying it by something that is a factor of 2. So, yeah, so that's the idea. So basically what we can do is we can divide out the GCD of these two numbers. And if we do that, then we're left with only things that we actually care about, right? So dividing out the GCD will give us a group of unique numbers, but we want to see when are those things always the same. So we can look at like, did I erase it? I guess I did erase it. So let's look at things modulo 7. So maybe we're looking at the numbers all the way up to 7, right? So we have the numbers 0, 1, 2, 3, 4, 5, and 6. And then I guess this is just the second sample. So we're going to take each number, we're going to multiply it by 6, and we say, what is its value modulo 12? So 0 times 6 is 0, 1 times 6 is 6, 2 times 6 is 12, but 12 mod 12 is 0. 3 times 6 is 18, mod 12 is 6. 4 times 6 is 24, which is divisible by 12, so it's 0. 5 times 6 is 24 plus 6, so it's 6, mod 12. And then 6 times 6 is 36, mod 12 is 0. Now you'll notice all of these are either going to be 0 or 6. They're all going to be divisible by 6. So we can divide out 6 from both of these, and now we have a 1 here and a 2 here. And that's the same as if we do all of this mod 2, we have 0, 1, 0, 1, 0, 1, 0. So all of these zeros will be in the same group. Basically, they'll all be equal to each other. We're counting how many pairs there are, so it's just the number of zeros to choose 2. That'll account for all the pairs. So the number n choose 2 is just n times n minus 1 over 2. So if we figure out how many zeros there are, how many 1s there are, how many 2s there are, how many 3s there are, we can iterate through each of those and do n choose 2. There might be a lot of things to iterate through though, so we have to be careful with that. So what we can notice is if we have something like this, maybe for a bigger mod, it'll look something like this. It'll be like 0, 1, 2, 3, 0, 1, 2, 3, 0, 1, 2, 3, and maybe 0, 1, and it stops there. Or maybe 0, 1, 2, and it stops there. So we're missing this 3 that we don't actually have. So this is our entire array. We can figure out the total number of groups by just n divided by 3. So that means we get 3 of these full groups that are of like all of them. And now n modulo 4, sorry, n divided by 4, because each group is size 4. So then we get 3 groups. If we take n mod 4, we get 3, which correspond to these 3 groups. That means these 3 groups will be 1 bigger than the rest of the groups, because they get this 1 extra thing. So what we can do here is we have 3 groups of size 4. And then we also have 1 group of size 3. Now we'll only have two different sizes possible because we like distribute the mods equally. That's how this works if you like count up under mod. So yeah, so like we just calculate 4 choose 2, and then we calculate 3 choose 2. We multiply 4 choose 2 by 3. We multiply 3 choose 2 by 1. Then we're set. Cool. I think I did a decent job explaining that. So let's move on. It's problem E. Okay, problem F is a bit tricky. So you have a bunch of segments, and then you have like basically you have a bipartite graph, but you have a like restriction on it. So it's pretty much a bipartite graph, but each one of these elements on the left connects to a continuous range of elements on the right, or connects to like a continuous range of segments, and then you have a bunch of elements on the right where each element on the right connects to a continuous range of things in the middle. So basically what you need to do is like find, assuming the answer actually involves flow, which is the path I was going down, the thing that you're trying to do is find a continuous, like update a continuous range here with edges in a fast way. Now, if you just wanted, like, if all of these left things were points, then you could do this pretty easily by just doing a segment tree add. So you could add to a bunch of nodes in a segment tree. Yeah, so like you could build, let me explain that a little bit better. You can build a segment tree over these nodes that looks something like this. So like here's your segment tree. It's got a left child and a right child, or you know, if you turn your head, one way's left, one way's right. Yeah, so you've got this like imaginary segment tree that we're building. Now, if we want to add edges to a continuous range of nodes on this side here, we can do that by adding to only a couple segment tree nodes. So namely, just because any range intersects log n segment tree nodes, then you can do the same thing by just picking a couple segment tree nodes, and that can represent any range in only log segment tree nodes. So you can add log n edges from this node here, and then that can represent some continuous range. And then you can do a similar thing on the right side. So at the very least, what you could do is you could like make two different segment trees, and like, well, yeah. So basically, you just need to find a way of representing these edges so that they're directed in the right way. Like these edges have to be directed this way. The reason in contest I made them bidirectional, but the issue is if you're trying to put flow to this node here, you can like push flow backwards up here and down here, and now you're matching with a range that you don't actually associate with at all. So these have to be like directed edges. That's important. And then but on the left side, we want these to be like kind of backwards, right? Because if you associate these line segments on the right side with continuous ranges, then you get something like this. So here, this will be associated with like some range like this, but you want that edge going this way. And you also want it so that no matter where the flow is in this range, it can always reach him. So you could do something like this. I'm missing a node. So if you direct the edges like this, then no matter where the segment tree node gets directed to, it has some path that you can go through the segment tree to get to all of the nodes that it actually should. So this is like order n nodes here, because each segment tree has a linear number of nodes, and then you have n times log n edges. And the idea is by doing this, we can make two segment trees and we can add edges between two ranges of nodes. that intersect. And that's what the problem is, right? Like, we have this line segment covers a range of values. This other line segment also covers a range of values. We want to add edges between all things that intersect. So that's kind of one way of doing it. And yeah, so this would be the number, like the size of my flow graph, and then I run flow on this. That might be too slow. There might be some way of doing this that doesn't involve flow at all, that takes advantage of like the properties of the graph. If there is, I didn't figure it out, so I don't know. But if this is the intended solution, this is very cool, I think. So yeah, I enjoyed the problem at least. Yeah, it's a bit tricky. It kind of like requires already knowing segment tree flow. And if you're familiar with segment tree flow, then I guess it's not too bad. Yeah, so if this is a new idea to you, hopefully this made sense. If you're already familiar with it, then you almost certainly knew kind of how this works, and this graph should help. I didn't actually solve it, so it's possible that my idea for that's just wrong. You never know. And then there was one more problem I didn't solve, or even read for that matter. But it looked like it was pretty hard. Okay, so good job to Geothermal, I guess. He was top of the people who didn't solve set. Umnic won. I guess not really any surprise there. And nice job to William getting top 20. Monaghan and I are top 100. It's always good to see. And yeah, I hope you did well as well. Not top 100, that's fine. You know, there can only be 100 people in the top 100, so you'll knock some people out eventually if you keep practicing. But I hope you enjoyed the set. I thought the problems were really good. Occasionally for educational rounds, they're not quite as good, but I thought this one was very interesting. Tough math set, but that's fine. And yeah, that's all. Hope you enjoyed the problem review. Have a great day. Goodbye.